How does transient conduction work in materials? Imagine touching a hot pan and feeling the heat spread through your hand. That quick change in temperature is a perfect example of how heat moves inside materials over time. When heat first contacts a material, the temperature at the point of contact jumps suddenly. But inside the material, the temperature doesn't become even all at once. Instead, heat begins to flow from the hot area to cooler parts, creating a gradual change. This process is called transient conduction. During this period, the temperature inside the material varies both with location and with time. The hot spot cools down as heat moves inward, while cooler regions warm up. Over time, the temperature differences lessen, and the material reaches a new balance, called thermal equilibrium. Transient conduction is governed by a mathematical rule called the heat equation. This equation describes how temperature changes over space and time inside the material. It takes into account how well the material conducts heat, how much heat it can store, and its physical shape. The rate at which heat moves depends on several factors. Materials with high thermal conductivity, like metals, transfer heat quickly. Materials with high specific heat can store more heat, so they take longer to change temperature. The shape and size of the object also influence how fast heat spreads. A common example is touching a hot stovetop. Your finger quickly heats up at the contact point, but the heat then moves into your finger's tissues. The temperature inside your finger changes over time until it reaches a new steady level, or you remove your hand. Understanding transient conduction helps engineers design systems that experience sudden temperature changes. For example, it helps in designing engines that warm up quickly, electronic devices that cool down safely, or materials exposed to quick bursts of heat. In essence, transient conduction describes how heat moves inside a material during the period when temperatures are changing. It involves a dynamic flow of energy that continues until the material reaches a stable temperature distribution. This process is essential for predicting how materials respond during non-steady heat transfer situations.